Hey everyone, this is Adam Kelly. This video is part of the Unity coin collecting platformer series. If you haven't been following along, you can find a link to the playlist in the description. Otherwise, open up your project and we will jump back in. Let's get started on our simple character controller. So we'll open this in Visual Studio, and then just to start with a blank slate, let's go ahead and delete everything that's in between the two curly braces here. We're going to start off by adding some variables that we can actually change from inside the Unity editor. And so that's why you're going to see some additional sort of syntax that's going to show off what these things are for. So we'll start with square brackets here, and we're going to write tooltip, and then in parentheses, we're going to add a note for what this actually does. Maximum slope the character can jump on. And then we're going to limit this to a range. And the range will be from 5F to 60F. Okay, so what does this mean? Actually, I'll explain it after we finish writing the variable. So we're going to create a public float called slope limit and set that equal to 45F. All right, so just a really quick explanation of what this does. It's going to create a tooltip so that if we hover over it in the Unity editor, it's going to say maximum slope the character can jump on. It's going to limit this to a range between 5 degrees and 60 degrees. And what the F means is that it's a floating point number. And you can look that up if you're curious, but basically it just means we can have decimal values. It's not limited to 5, 6, 7, 8. We can have like 5.5, 6.7, 6.7183. You get the idea. And then the default that we're setting this variable to is slope limit is 45 degrees. So if I save this with Control S and then go back to Unity, it's going to update and recompile these C# scripts. And then if we come to our cactus character, let's go ahead and drag this script onto the character. So it should go underneath your capsule collider. Then now we're going to see that slope limit variable is something that we can change. And it automatically capitalizes it and adds spaces for us. But now this variable, if I were to change this to 17.3, you're not going to see it in the code, but this variable will change. So you can experiment with different variables for slope limit. And what slope limit is in this case is basically we're going to have a character that can stand on slopes. And if it's on too steep of a slope or a hill, then it shouldn't be able to jump on that anymore. There's a limit to it. So if you didn't do that, you'd be able to jump up slopes that are like, 80 degrees steep, and that's just not realistic at all. So that's what that variable is for. And I will just go back here and change this back to the default because 45 is a good value. And while we're here, let's also connect the input controller. So what these are going to do is basically they will run whenever play is pressed. So we don't have any code doing anything right now, but these are set up so that they're attached to the character and they will be able to do things with the character. So back here, let's go ahead and add a few more variables. And I'm going to go a little faster this time. We're going to create a new tooltip. And we're going to call this move speed. So we're going to say move speed in meters per second. And then public float move speed equals 5F. Okay, so this is the second variable here. And just to go back in here and just show this really quick. Now, when we click on our cactus character where you have the scripts attached, now we're going to have this value that we can change as well. So I didn't do a range on this one. Technically, you could set the move speed to whatever you want, but a starting move speed of 5 seems pretty good. Now I'm going to speed things up a little bit because you don't want to just sit here and watch me type this stuff that doesn't need explanation. I'm going to copy this from another project I have on the side and paste it in. And you can pause the video and make sure to add all of these variables as is. Make sure that the capitalization matches. Make sure that you don't accidentally copy and paste and get the variable type wrong. A bool is just a true or false value, so it's different from a float. And once you have all that, you should be able to go back into your project and you'll see all of these things are set up here. We're actually going to turn on allow jump. And also, as I mentioned before, you can hover over these and you'll be able to see those tooltips. Now we need to add a few more variables, and I'm going to try and speed things up by just copying and pasting them from a project I have on the side. And what these are for is, in this case, these 4 variables here are for movement related things, but we're going to access them from the input controller, at least in the case of these 3. So these are called accessors, and that's why they look a little different. Basically what it means is we're going to create this variable. It's public. You can get it from anywhere, but you can only set it internal to this class in this case because of this private set. So the only thing that can change this variable is this code. And that's going to be useful because isGrounded is supposed to keep track of whether the player is on the ground. Basically, whether it's allowed to jump or not. If it's grounded, then we are going to say, yes, if you press the space bar, it's going to jump. If it's in the air, or if it's on a really steep slope, we don't want to be able to still jump again, because otherwise you could just hold down the space bar and then you would just fly up into the sky forever, which might be fun for a minute, but probably isn't very useful for your game. So that's what that's for. This forward input and turn input and jump input, these are all for your character's movement. So we're taking in whether the character's moving forward or backward, turning left or right, or jumping. And so the input controller is going to set these values so that we can use them in this class. Now, this right here, we're creating new variables to keep track of the rigid body and the capsule collider. So that's just these right here. Basically, we're going to query the class itself. We're going to look for this object, and then we're going to find rigid body and capsule collider on here. And then we're going to save them into these variables. And the reason we put new in front of this one is because Unity has some legacy code that used to be able to access rigid body just by calling .rigidBody on an object. And we want to reuse this variable here. So we're just going to put this new thing here that'll suppress a warning message, basically, that's saying, hey, you shouldn't do that, but it's fine. And then this one is keeping track of the capsule collider. These are both private. They're not going to be accessible outside of this class. And so let's go ahead and add these basically to a function that's going to be called as soon as the code starts. We want to find these and then keep track of them. So we're going to call a new function called private void awake. And it should suggest this to you because this is a special Unity function that is called as soon as you press play, as long as it's attached to some object in the scene. So because we have this attached to our cactus character, then this should be called as soon as we wake up, basically. So if you were to do a log statement, so the way you can log to the console is with debug.log, and then you can say something like, I'm awake. And then you have to put a semicolon at the end. Then you can save your code, go back to Unity. If you press play and you go to your console tab here, not the project, but the console, you should see something pop up here that says, I'm awake. So that's how logging statements work, and just shows you that this code is being called automatically as soon as things happen. If you create other things that are not special Unity functions, they may not be called automatically at all. You have to call them yourself. So go ahead and delete that. And we want to basically just set these two variables. So rigid body, and make sure you get the lowercase version of it, that you don't do an uppercase version. This is matching with this variable name right here. And set it equal to get component. And we're going to say rigid body. What this means is get a component that matches the type of rigid body. So that's why it's capitalized here and lowercase here. This is the variable name. This is the type of object that we're looking for, the type of the variable. And then do a semicolon. And we'll also do the other one, capsule collider equals get component. And then in these angle brackets, we want to find a capsule component, or sorry, capsule collider, like this. And so again, this is the variable name. It's got a lowercase c. And then this is telling it to find a component called capsule collider on here. So what's going to happen is when we call play, you won't be able to see it, but basically it's going to look on here for the rigid body and the capsule collider and then give us access to that. So just for a quick test, we can maybe let's check the mass of the rigid body here. So if we were to do debug.log and then we called rigid body.mass, then it should log that mass to the console when we click play. And there it is, 100. So that's what we're doing here. We're just saving these into some variables. Let's go ahead and delete this. We don't need to log that every time. And we should be able to access this much more quickly. These get components are useful, but they're not so efficient. So you don't want to call them as often as we will need these two things. Let's add a function that can check whether the player is grounded or not. I'm going to do some copying and pasting so that I don't have to type everything, but I'll explain everything as I add it line by line. So I'm going to start by creating a new function here. And when I copied and pasted that, it moved my curly bracket on me. So let's make sure that we've got a matching curly bracket here. And I added a comment up above that says it checks whether the character is on the ground and updates is grounded. So it's going to update this variable here based on whether the player is touching the ground or not. And I want to just cover really quick what I mean. This is a tutorial that we have on the Immersive Limit website that I did for a simple character controller. It's the same character controller we're using here. And the concept here is that our player is going to be in a capsule. So this is the capsule that you're seeing right here. And then whether it's on a flat ground or a slope, it's going to do a raycast downward. So this red line right here is representing the downward raycast. And we want to know whether this hits ground or not. The interesting thing that needs to happen here is if it's on a slope, we need to cast more than just a little bit down. But if you think about it, this can actually cause some problems. How far down should we raycast? We could pick like just a static amount. But the problem is if you're on a slope that's too steep and your player is sliding down it without being able to jump, that might not be desirable. However, if this raycast is too long, you can end up having some cases where it's able to actually slide up really steep walls. Or it might still be grounded while it's actually, let's say it's a few, I don't know, maybe 30 centimeters in the air or something. And if we've made a raycast that goes down and tests whether the ground is anywhere within 50 centimeters, you're still able to jump even if you're off the ground. So that can make for some weird behavior that we don't want that. So the idea is that we're going to have a raycast that tests based on the actual desired angle that we have. It's going to hit the ground and use basically a normal vector to determine whether this is a slope that it can actually be on. So we're going to start out by setting our isGrounded variable to false. So we're going to just default to assuming we're not grounded until we prove otherwise. Next, we're going to set a variable called capsule height. So float capsule height. And we're setting this equal to the maximum of one of these two values here. So it's either going to be the radius of that capsule collider times 2, or the capsule collider.height. So we're looking for whichever one is taller. And this is because of the way that the capsule collider works. If you make the radius of basically the spheres or the hemispheres on either end of it too big, they'll actually be taller than the height that you try and set for your capsule collider. So it's possible that if your radius is larger, you could have two hemispheres making up essentially a sphere that ends up being larger than the height that you set. So that's why we have to take this radius times 2 and get the maximum of it. Next, we're adding a variable called capsule bottom. And the idea here is we want to know exactly where that bottom point of the capsule is, so right here, so that we can shoot a ray down from that location. So this is transform.transformPoint, and this is just so that we can place a point in space correctly, and that's based on the center of the capsule minus that capsule height. So we're basically saying we know where the center of this capsule is. We just want to or basically place a vector downward and then divide it by 2 of the capsule height. That should give us that point in space. Next, we have a variable called radius. We're going to set this equal to we're going to transform a vector in this case. And so this is basically transforming it into world space of the capsule collider.radius. So this is essentially giving us the actual radius of this in world coordinates, because it's possible that the actual radius is different from what the radius of the capsule says it is. You can imagine this can happen if the object has been scaled at all. We want a real radius of it in world coordinates, and that's why we're doing that. All right, now we're going to do our raycast here, and this should be pretty straightforward. We're going to start out with a ray, and that's going to be declared as new ray, and we're going to use capsule bottom plus transform.up times 0.01f. Okay, so what this is doing is basically it's creating a start point that is slightly above the bottom of this capsule. And then we're going to cast it downward. So in the negative up direction, that means it's downward basically. And it'll be 1 meter long because up defaults to basically just a unit vector in the down direction because we've negated it. Next, we need to create a variable called raycast hit. And what this will do is it will hold the output information from this next piece that we're going to add here. So we're going to do this if physics.raycast ray out hit radius times 5. Okay, so this is basically saying, this returns true or false based on whether it hits something. Okay, so we are going to cast a ray downward, and the ray will be this guy right here. If it hits anything, it'll put the raycast hit information into this variable. That's what this out means. It means it'll call this function and put some stuff into here. And then the distance is 5 meters down, or rather it's the radius times 5. So not necessarily 5 meters down, but it is a safe distance from the bottom of this spherical shape at the bottom. So we're going to cast quite a ways down. So in this case, if the radius was, maybe half a meter or something, it's going to shoot it down 2.5 meters. So that should give us plenty of room. And then we want to do some checking here to see if it's the right length, the right distance. So we're going to start off by calculating the normal angle, and that is this right here. This blue vector right here is the normal. It's sort of just whatever it hits, which direction is that facing? And we set that to vector3.angle, hit.normal, comma, transform.up. What that means is we're going to get an angle between that normal vector that the raycast hit versus the up, or between the up vector and that normal. It's basically what we're doing here. And then what we want to do, and this is kind of the main point of it here, if the normal angle is less than the slope limit, then that means we're on a slope that we can successfully jump on. It's not too steep. So we've determined that it's not too steep, but not that we are actually grounded yet. So we're going to say, we're going to create a new variable called max dist, and that's just going to be the maximum distance that we can possibly be from. Basically, it's what is the maximum distance this can be from here to here while on a slope of this height and still technically be grounded, because it's actually grounded over here in this case, but we are doing our raycast from here. As long as we're on a flat plane like this, though, you can imagine this thing becoming steeper or shallower, and then we're able to basically just extend this red line accordingly, and we're still technically grounded. So that's what we're checking here, is what's the maximum distance we could be away and still be grounded on this surface. And that's going to be the radius divided by the cosine of the normal angle here, minus the radius plus 0.02f. I'm not going to explain exactly how I got to this, but this is basically how I calculated it. It's some pretty simple trigonometry. And then finally, we're going to do our last check here. We're going to say if the hit.distance, so that's the distance that the hit is away from the origin of that raycast, is less than that maximum distance, then we're going to say is grounded equals true. If any of this is not the case, if we don't hit anything, if it's not less than the slope limit, and if it's further than the distance, then we're going to just default to is grounded equals false. So I know that was a lot of code. I hope that it made sense to you. It's kind of a lot to digest if you're newer to coding, but if you need a little extra explanation, then this tutorial on the website should actually be quite helpful. We'll make sure to link to it in the resources, but if you're looking for it, it's this simple character controller for Unity. And I do some more explaining of it. It might be a little more helpful than just listening to me talk about it. Now we're going to write the function that's going to process actions. I'm going to copy and paste this again. And we'll start off with a new function declaration here. And as the comment says, it processes input actions and converts them into movement. So it's called private void process actions. And then we, of course, need our curly braces again. And what we'll do first is we will process turning. I'm just going to copy this whole section here and explain it. So what we're going to do is check if turn input does not equal 0. Now, if you remember earlier, I said that turn input is going to be set by the input controller. So that's what we're checking here, is what's the latest update on turn input. If it's not 0, we want to calculate the angle that we're going to be turning. And so what that does is basically we clamp the turn input between -1 and +1, and we multiply by the turn speed. So that tells us what angle we're going to change toward. And then we're going to say transform.rotate, We're going to rotate around the vector3.up angle, or vector rather. And then we're going to rotate based on the fixed delta time. Okay, so that is basically the time between fixed updates, which you can think of it as something that happens every, I think it's 0.02 seconds. It's just a function that gets called over and over and over and over and over again as the play continues in the game. And so we're going to basically be multiplying this angle by 0.02 so that we only move a slight amount on each update. Fixed update is also where physics happens, which is why we're going to be doing this inside of fixed update. Same goes for this. We'll be checking if it's grounded every 0.02 seconds. Next, we're going to check whether the player is grounded, and then we're going to do different things accordingly. So I'm going to create an if-else statement here. And we're going to do first some basic like sanity physics stuff here. So we're going to reset the velocity first. So basically, anytime we're processing actions, we're going to make sure that we set the existing velocity to 0 so that we can then apply our own velocity to it. Next, we're going to check if we're trying to jump. So we check that jump input variable that should be set by the input controller. And we also check whether we have allow jump enabled. So that, if you remember, was something we defined up here, allow jump. And so that's, if you don't want the player to be able to jump, then you can turn this off. If you want the player to be able to jump, you can have it on. So we're going to apply an upward velocity to jump if both of these things are true. Also, keep in mind this is in the if is grounded. So we have to be grounded, jump input has to be pressed, and allow jump has to be enabled. And if so, we're going to set the rigid body's velocity. We're basically going to update it by adding the up vector times jump speed. So we're starting with a velocity of 0, and then we're adding this up vector. So it's essentially just setting it to the up vector times the jump speed. After we've done that, we're going to apply a forward or backward velocity based on player input. So this is going to be basically just adding velocity to the velocity we've already created. So in this case, we're already jumping, but we also want to take into account whether we're trying to move forward or backward. And so we're multiplying that by the forward input times the move speed. That's all we're going to do if the player is grounded. Okay, so basically if we're on the ground, we can walk backward and forward, and we can jump. But if we're not grounded, then things have to happen slightly differently. And I'm going to paste kind of a bigger chunk here and then explain. So the first thing we have to do is check if the player is trying to change forward or backward movement while jumping or falling. Now, in video games, you may not think about it very much, but you are able to generally control your fall. So if you're jumping in the air, you can still kind of move forward or even pull back mid-jump. But in real life, obviously, we can't do that because we have nothing to push off of. It's just a convenience that video games afford us, and so we're going to account for it here. So we're going to first check to see if basically what this is saying is forward input approximately 0? But we're negating that. So we're saying if the forward input is anything other than 0, then we're going to override the forward velocity with player input at half speed. So we're not going to allow them to move at full velocity forward or backward while they're falling or jumping. We're going to allow them to move at half speed. And so we have to first calculate that vertical velocity so that we can use that. So we're projecting this existing velocity onto the up vector. So if you think about this, what we're basically doing is we're saying basically how much of this velocity is up and down versus anything else. We're isolating it to just the up by projecting that vector onto that vector 3.up. And then we have to add that vertical velocity to the forward move speed divided by 2. And then that becomes our rigid body dot velocity. So the reason we do this is we want to keep any existing falling velocity that's happening, or even upward movement if we're still kind of at the first half of our jump. And then we add that to any forward movement that the player invokes. And as you might have noticed, this is all after turning. So turning can happen regardless. You can turn around in the air if you want to. We don't stop that from happening. We don't even use physics to do it. The physics is purely restricted to the jumping and the forward and backward movement here. Finally, you might be wondering when these things are going to be called. And we're going to do this inside of fixed update. And I'm going to put this right after the awake function. I find that it's helpful to keep them organized that way. So we're going to say private void fixed update. And this is different from update. So update is when you basically every time there's a new frame that's rendered. And that doesn't happen as frequently as fixed update. And so if you want to do anything related to physics, you don't want it to be reliant on your frame count, because then you've got some weird potential issues that can happen. You want to restrict it to anytime physics is updated. So in fixed update, we're going to call first check grounded, and then we're going to call process actions. So what it does is it calls this function, it checks whether it's grounded, and then it's going to call process actions and take in any player input. And that's all for the simple character controller. Hey, we really hope you're enjoying the course so far. If you are, make sure to check out the rest of our courses on immersivelimit.com. There's other Unity and Blender related game development stuff that you'll probably be interested in. Thank you so much for watching, and we'll see you in the next video.